We have already walked through a scenario where you have a load instruction and how reading from the memory works with direct mapped cache. Let's now go ahead and think about the store. What happens when you try to write to a direct mapped cache? Let's discuss what we have when we have a write, for example, a store instruction. I have written an example here where we have this register X220, which we are saving in address A. And let's assume that, for example, X20 has some value, let's say 100. Before the execution of this store instruction, A had some value, let's just, for example, say 300. Now, when the CPU issues this instruction store, it's going to go to to the cache, not the memory directly. We have discussed this before. And it's going to first check to see if this A has a tag that matches the tag in the cache. If the tag matches, then you have a hit. Otherwise, you will have a write miss. If we do have a hit, we simply update this data position to the value 100 that we are asked to store. Now, if you don't have a hit, you have a write miss. When you have a write miss, you have to go to the memory, bring the data back from the memory, read the data, bring it back, and save it in the cache before you can update it. So I'm going to update to have the value 300. I'll update the tag so that it has the tag of this address A. And now my cache matches the memory, and now I can go ahead and update it. Now that the cache matches the memory, I can go ahead and remove this 300 and update it to 100, which is the value we were trying to store. So the store has happened now in the cache. We are at the same sort of situation where we were if we had a hit. Now that issue is fixed, that number 100 is here, but there is another issue that is not fixed. And that issue is that now we have a discrepancy between the cache and the memory. In the cache, we have number 100. In the memory, we have number 300. And the discrepancy is because we have updated the cache, but we haven't yet updated the memory. And we need to come up with a solution to it. There are three possible solutions for this discrepancy, and we are going to go through those three solutions in the rest of this video one by one. Okay, so the simplest thing that you can do when you have a write is what's known as the write through scheme. A write through scheme says this. Basically, whenever you have a store, you should go all the way from the cache to the memory and update the memory as well. Every update to the cache has to be synced up with the memory. So as soon as we updated the cache here to have the value 100, if we are using a write through a scheme, we should go back to the memory and update the value to be also 100. And now they have the same value. So what's nice about write through a scheme is that it's very simple, right? You know exactly where that the cache and memory are always synced up together. They always agree with each other. There is no extra complication. The bad thing, of course, is the performance hit, because the whole point of cache was for us not to go to the memory. If you're using a write through system, you still have that with loads, but with stores every single time you're going to go to the memory. And so your performance is going to be hit terribly. So in that sense, it's not so great. We are going to look at some of these examples during the online class. Another alternative, the second scheme is called the write buffer scheme. The write buffer scheme says this: let's put a buffer right in between the cache and the memory. What's a buffer? A buffer is a small amount of memory that acts like a queue. So unlike, you remember when we learned about the stacks, we said they are first in, last out. A queue is always a first in, first out, and buffers are implemented using queues usually. So the moment we update the cache, instead of going all the way to the memory, we go to this buffer and we write it into the buffer. It's much easier to write something into the buffer than writing it to the memory. Why is it easier? The reason it's easier is that the buffer is a small amount of memory. It's not big. So we'll just write the number 100 over here. And there is a separate controller which is going to basically, its job is to read things from this buffer and write them to the memory. But the cache does not need to wait for that buffer to do its work. The cache can simply return to the CPU and report that it has finished the storing. This writing to the buffer is going to happen at some point in time. If another store comes, so this will be delayed, right? So the memory is going to get updated with some delay. If sometimes goes by and then there is another store, let's say the next instruction is another store, this new store is going to be added to this buffer, right? Because it's a queue, it's a first in, first out. This thing is going to move ahead, and the new thing that is being written is going to be added to the queue. In the order that these requests for storing are received, you are going to add them to the memory. Now, the rate, the speed at which things are read from the buffer and written to the memory is a lot less than the speed at which instructions are being issued here. What that means, let's assume, for example, that you have only a buffer of only 4. Your buffer has only a space for 4 things. A buffer always has a limited space. If you have 4 stores in a row, your buffer is going to be full. What do you do when the buffer becomes full? Well, you have to go back to stalling again, right? When the buffer is full, you have to stall until the buffer is empty again, right? So, for example, if I move, if you have 4 stores in a row like this, and they have all been accumulating in the buffer, at this point, your buffer is full. If I get now one more store instruction, I don't know how to deal. I wouldn't be able to deal with that. I would have to install the CPU over here and then go back. So this buffer system, write buffer system, works perfectly fine when the rate at which you see the store instructions is not very high. Maybe you have, for every store that you have, there are several instructions until you get to the next store. Or maybe you have 2 or 3 stores in a row, but then not a lot of the other one. Basically, if you think about the rates, the rate at which you are trying to do writes should be lower than the rate at which the data is being written from the buffer to the memory. If that's the case, then you are good. So the last scheme strategy that we want to discuss is called write back. Write back is actually a very clever idea. This is what write back is. Remember that every time CPU is trying to read from the memory, it's going to first go to the cache. It's never going directly to the memory. We are always going to cache first. Because of that, why don't we actually allow the cache and the memory to be completely out of sync, right? I'm not going to go to the memory. So let's just keep the correct value in cache and not update the memory right away when you have a store. Okay, so we allow this inconsistency between the cache and the memory to persist, at least for a while. Now, because there is a consistency, at least at the minimum, right, we have to know that there is a consistency. So we are going to add yet another bit to our cache table here. It's going to be 1 bit. It's called the dirty bit. When you update the value of some block so that it is now inconsistent with the memory, we are going to set this dirty bit to 1. So initially it's 0. Now I have updated it to a 1. So what that means is that I know that the value that I have here is inconsistent with the memory. Why is this useful? Here's the thing. At some point in time, you might take out so right now, the tag here is tag of A, which means this position is in memory is mapped directly in this position of cache. But later on, at some point, you might decide that you want to replace this cache line with some address other than A. I just paused the video and I updated this figure. I moved what we had before to the top and I draw this thing on the bottom. Time goes by. After a while, now we have another store instruction. This store instruction is address B, but imagine that address B and address I both have the same index. They are both mapped to the same row. Right now, from before, what we have is data is A here and 100 here, and you have the tag of A over there. The dirty bit is 1, and the valid bit is also 1. This is our current state. Now, when you get this new store request, or it could have even been a read LDUR, right? Even if it was an LDUR, you would have exactly the same scenario. Either one of those. You would, okay, so you go to the cache, you look at the index of B, it's over here, but you have tag of A, so you have a miss. When you have a miss, you have to go to the memory and get this value and bring it to the cache. However, so normally you would just throw out A and replace it with the value of B over here. But now you cannot do that. Why? Because you have this dirty bit equals to 1. If you throw out this number 100 from the cache, it's going to be lost forever. You are not going to have any way to recover that. So when the dirty bit is 1, before I update this with the value of this new memory address, I first have to install. So I'm going to tell the CPU that you have to install. Why do you have to install? Because now I want to go back to the memory and update it. So I'll go back to the memory. I update the value to the value that I have in the cache. The value that I have in the cache is 100. I return. Now that I have returned, I can copy the value of B over here. Right, so I set this dirty bit to 0. I change this tag to be tag of B. I copy the value of B here, and my valid bit is a 1. This is what you get if you had a load instruction. Now, if it was a store, then what you would have to also do after this is, again, update the data to 600, which is the value that is being stored. I would then also set the dirty bit to a 1 again. Again, you set it to 1 only if you have the store, right? But when you bring something in, the dirty bit is going to be initially set to 0. So the bottom line is that the dirty bit is either 1 or 0. If it's a 1, it means that the cache line is inconsistent with the memory. If it's a 0, it means that it is consistent with the memory. Everything is fine. When it is a 1, before you replace something in the memory, you have to install in the cache. You have to install the CPU, write what you have in the cache back to the memories, hence the name write back or copy back, and only then you can continue with the normal execution. The write back scheme is one of the better schemes. It's very efficient. Why? Because you don't write back things to the memory right away. You only do that when you have to update the cache, when you're throwing something out of the cache. So that's the main benefit that we get from write back. And in fact, if you want to look at the design of a write back, this is basically what I was drawing, right? This is our previous design with the full block. We now have added a dirty bit as well to it. Nothing else changed if you have this write back scheme, except that you need to add this dirty bit.